All right, here we are. It is, I guess it's April Fool's Day. If we were in the classroom, I'd have something special planned for you, but I don't think it's going to fall properly in a video, so I'll save it for when I see you. So, we're going to extend what we learned in section 4.1 about extreme values. And over there we had a theorem. And this is the corollary to that theorem, which is just an add-on to the actual theorem. That's what a corollary does. So we let f of x be continuous on some interval ab. And okay, so if the derivative on this interval, if the derivative is greater than 0 on this interval, then the function is increasing on this interval. Right? So if the derivative is positive, that means it has positive slope, then the function is increasing. So you can imagine it. If this is the function f, all the derivatives here are going to be positive because the slope of the tangent line is in the positive direction. Similarly, if the derivative is less than 0 on AB, then f is decreasing on AB. Okay. For the same reason, so if the function f is going down, then any tangent line along there is going to have a negative slope. All right, so let's look at an example. We're going to let f of x be the function x cubed minus 12x minus 5. And we want to find the intervals where f is increasing and or decreasing. Okay. All right, so step 1 is to find the critical points. All right, compute f prime of x. You get what? 3x squared minus 12. And set it equal to 0. And this is true if and only if 3 times x squared minus 4 equals 0. And that factors nicely. And so we get the critical points. X equals plus or minus 2. And those are our critical points. That's what the derivative is 0. And so now we use this great tool called a sign chart, because all we're looking for is the intervals where it's positive or negative. And so this is how you do the sign chart for f prime. You make something like this. This is a sign chart. F prime. And this is just the real number line. So we're going to plot our two critical points there at minus 2 and 2 and make dashed lines here. And what we do is we parse this function or this derivative out. So first we look at this piece, right? Put that piece. And a quick calculation will show you that x minus 2 is positive to the right of 2 and negative everywhere else. Okay. And then you plug in you list the next monomial there. And you go, okay, where's this guy positive? Well, it's positive to the right of minus 2 and negative elsewhere. And then you go, all right, f prime is just the product of these two with the 3 in front, which has no effect. So a negative times a negative is a positive. A negative times a positive is a negative. And a positive times a positive is a positive. Okay? So on this interval, f prime is greater than 0, so f is increasing. And so we have increasing on minus infinity to minus 2. On this interval, f prime is less than 0, so f is decreasing, and that's the interval minus 2 to 2. And then over here, f prime is positive, so f is increasing, and we have 2 to infinity. So to answer the question completely, we go f is increasing on minus infinity to minus 2 union with 2 to infinity, and f is decreasing on minus 2 to 2. Okay, so this sets us up for the first derivative test, which is a consequence of this corollary. Okay, and again, same assumption as the corollary. Let f be continuous on AB. So this is part 1. If f prime of x goes from positive, so increasing, to negative at some point x equals c, and it's important to note that f prime of c is equal to 0 or undefined. It's a critical point. So if f prime of x goes from positive to negative at a critical point, then this is a local max. Then f of c is a local maximum. Right, so in 2, if f prime of x goes from neg to pos, so from negative to positive, at x equals c, same, again, critical point, then f of c is a local minimum. And if there's no change, well, then it's neither. Could be something else. A lot of times it turns out to be what's called an inflection point, which we'll leave for later this week. Okay, so let's do some more examples here and then some guided practice. So, well, let's just continue the last example. So minus 2, f of minus 2 is a local max, right? Because we went from increasing to decreasing. And 2f of 2 is a local minimum because we went from decreasing to increasing. Okay, here's another example. This time we're going to start, let's say we had a function f and we did some mad math here and we computed the derivative, factored it, and got this. We got this factored form, x minus 7, x plus 1, x plus fine, and we were asked to to identify local max and mins. Okay, so I'm trying to get you comfortable with this sign chart. Okay, so it's a sign chart for f prime. So the critical points are -5, -1, and 7. Our monomials are x minus 7, x plus 1, x plus 5, and then the derivative is just the product of these three. Okay. So we fill in the sign chart one at a time. That guy goes like this. This guy goes like this. And this guy goes like this. And then we do the multiplication. We have negative, positive, negative, positive. So the function is decreasing on minus infinity to -5. It's increasing on -5 to -1. It's decreasing on -1 to 7. And it's increasing on 7 to infinity. So we have a local min at -5, f of -5, and -1, f of -1. And a local max at hold on, that was wrong. I can't see the I can't see the numbers. It's 7. So this is 7. F of 7 and a local max at -1, f of -1. Okay. Your book handles its sign chart a different way. I don't like it. It's not the better way I think this is, but it's up to you what you choose. If you follow the book or you learn from someone else, as long as it works, I don't care what you use. Okay. All right. So here's our first guided practice. Let f of x be x squared minus 3 times e to the x. So you want to find local max mins and intervals of increase and decrease. Okay, so pause right now. Have a go and see what you come up with. Okay, well, hopefully that didn't take too long. Let's see here. First we start by finding critical points. So we're going to take the derivative. So f prime of x is, so we're gonna fix this and take the derivative of e, and then take the derivative of this and fix the e. And this becomes e to the x times x squared plus 2x minus 3. Right, we set this equal to 0. Now, since e to the x is non-zero for all x, you can divide both sides of the equation by it. So both sides. And you get just the polynomial. which conveniently factors. Is that right? Yep. And gives us the critical points, -3 and 1. Okay. All right. So let's make the sign chart. We got -3 and 1 is our critical points. And it's important to note that this is the derivative. Which we broke down. So just for completeness, I'm going to put e to the x in here because that's part of it. And then I'm also going to put x plus 3. And then I'm also going to put x minus 1. And then we're going to take the product of these three. Now e to the x is positive anywhere, so it doesn't do anything to the sign chart. But I like to put it in there. And this should be a negative. So x plus 3 is positive to the right and negative here. 1 is positive to the right and negative here and here. So you have plus, minus, plus. Okay, so let's do the whole thing here. There's an interval of increasing. There's an interval of decreasing. And there's an interval of increasing. So we increase on minus infinity to -3 and 1 to infinity, and decrease on -3 to 1. All right, let's find these points. So -3, f of -3 is a local max. And what's f of -3? -3 squared is 9, so it's 6e to the -3. So there's your local max. And then one comma f of 1 is a local min. And what's f of 1? F of 1 is -2e. All right, well, the next section is about concavity and sketching curves, but I think we can muck around and get our hands on this, see where these points lie. So let's try and graph this thing. And we'll get better as the week goes on at graphing. So we know there is a minimum at -3, 6e to the -3. So we're just going to put it, I don't know what that number is. It's positive. That's all that matters. 3, 6e to the -3. Let's put a point there. And then we know there is a minimum at 1 -2e. It's going to be down here somewhere. There's 1 -2e. Okay. That's going to be a minimum. Okay. Do we know anything else about this function? Where's the y-intercept? The y-intercept is at -3. Hold on, I didn't label this very well. There's 1, 2, 3. All right, the y-intercept we got a couple of zeros at where? Plus or minus √3. So plus or minus √3 is about right here and about right here. So maybe this guy's a little higher. Doesn't matter. So this is a minimum. And this guy's a maximum, so it must be turning here. We don't have any more zeros, so it must be that this thing goes off to infinity. So there's my not to scale ghetto graph. Let's see what it looks like on Desmos. X squared minus 3. Where is E? Is it here somewhere? Exponential of X. Does that work? That's not bad. Let's go back to mine. So let's see if we can. Yeah, same. All right. Well, hopefully you got that. Maybe not the graph. We'll learn how to clean this graph up better in the days to come. And so here's guided practice number 2 to do before you see me in a few minutes. So it's x squared minus 3 over x minus 2. Same instructions, max mins, intervals of increase, decrease, and a good graph. We've learned how to graph these rational functions before, so